Thanks again for them setting this conference up. It's a great place to gather like-minded software architects together, so it's a great privilege to be here. So let's talk about what makes software architecture so intractable. Can we switch over to my slides there? Maybe. This worked great. There we go. Hey. How many software architects does it take to plug in a projector? So, what makes software architecture so intractable, which I realize is a weird word to be used at an international conference because it's not the most common English word, but I put the definition up there. Not easily controlled or directed, not manageable, stubborn, obstinate, of course. And when you look at the most recent several books I've written, it all really delves into this topic in one way or another. So let's talk about this. And I want to talk about it in two different aspects of software architecture. The structure of software architecture, how we design systems in software architecture, and then the mechanics of how we put software architectures together and do things like govern software architectures. So let's talk for a second about an interesting problem that this question about architecture versus design. This is an age-old question, and in fact, Mark and I, in our Fundamentals of Software Architecture book, very pointedly decided not to address this question because it's a swamp. There's no good answer to this question, and we figured that a huge part of the book would be just trying to untangle this impossible-to-answer question. But then, when we wrote Head First Software Architecture, the Head First books are really meant to be introductory books, and we felt compelled to really address this question because of that. And we'd also been asked this question so many times after the first book had come out because one of the obvious questions is, what is the difference between these two things? And what we realized was the reason this is such a difficult question to answer is that, like so many things in software architecture, it's not a binary. You can't point to something and say, that's purely architecture or that's purely design. So many things in software architecture instead exist on a spectrum. Decisions are somewhere on this spectrum between architecture and design. And it doesn't really matter exactly where on the spectrum it is, but it is illustrative because this helps you determine some important characteristics about the decision. So now this begs the question, well, what pushes things to the left and what pushes things toward the right? And Mark and I, when we created this, we have an interactive exercise in our classes, and we created this scale from A for architecture, D for design, and see how cleverly we use the alphabet to create this spectrum like that. And so, but the things that push it from one place to the other is, how strategic is this decision? How much is this decision going to impact the other decisions in our long-term direction as an organization, or how tactical is it? How much is it a quick decision that we need to make right now to solve a small problem, but we can fix that at some point easily in the future? What's the effort required, both to implement this decision initially, but also to change it later? Choosing an architecture style is classically an architecture level decision because it takes an enormous amount of effort to build the thing, and then it takes an even more amount of effort to change it later if you want to. Whereas design decisions tend to be much lower effort and therefore much more changeable. What about the trade-offs? How many trade-offs exist with this decision? Is it really significant? Well, I guess no trade-offs are really insignificant, but maybe less significant from a trade-off standpoint. This is how you decide where something falls on this spectrum to think about decisions in your architecture world, because obviously strategic, high effort, and significant trade-off decisions require more care and effort and backing. So we're considering using microservices for this new system. Well, Clearly, that's an architecture level decision because it matches all those things. It's highly strategic, takes a huge amount of effort, and there are significant trade-offs associated with it. What about we need the cancel button moved to the bottom of the screen? Classic user experience design kind of issue, very tactical, very low effort, and in this case, pretty much insignificant trade-offs. There are trade-offs in usability, but again, not many technical trade-offs. And those are low balls. Most decisions don't fall anywhere near the edges of those spectrum. And here's a great example of that. We're considering breaking the single payment service into separate services, one for each payment type. Well, this is using the philosophy of microservices to guide your architecture. But there's a problem with philosophy. It's not very useful for doing trade-off analysis because the philosophy of microservices says, well, it's supposed to be single purpose, right? Okay, great. But are all payments single purpose, or is each kind of payment single purpose? You could have arguments over drinks, and in fact, some of you may have that argument over drinks tonight, but it's not a good place to help you make decisions like this. And you may initially look at this and go, well, that doesn't sound too tough, but your instinct is often wrong about this. And so this is where your actual job kicks in. Because your job as a software architect is not to find silver bullets laying around where someone has hidden them for you and you can uncover them and you've got a perfect solution to a problem. That almost never happens. Instead, what your job is to do trade-off analysis. Your job, you do best benefit at your organization as an architect if you get really good at doing objective trade-off analysis. And in fact, sometimes you're not even the one making the decision, you're just doing the trade-off analysis to allow an objective decision to be made by you, other stakeholders, the organization, and other drivers in the organization. And so when you run into a problem like this, rather than just throwing a dart and picking in place, you should do trade-off analysis. And here's one of the techniques that we talk about in our Architecture of the Hard Parts book. Model relevant business use case scenarios and see what the trade-offs are by doing that. So we have a single service versus 3 different services. So let's model some relevant business use case scenarios. The first scenario might be we need to update the code for credit card processing. What kind of impact would that have? And what kind of trade-offs would that entail? Well, if we do that for the single service, I have to change the code. I have to probably potentially update a database schema. I need to test everything because I've touched some of that code and make sure it all works. Whereas for the separate services, all I need to do there is add a new service and, change that one service. Sorry, I'm updating credit card processing. Change the one service, highly decoupled, no rippling side effects to the other services. And so for updating credit card processing, separate services give me better maintainability, better testability, and better deployability. Okay, well, let's look at the second possible scenario. Add a new payment type. This is the one I was thinking about. For the single service, let's say we're going to add reward points as a payment type. So for the single service, I come in and add reward points, which means I've made a change, which means I need to test and check the data and the code and make sure everything's working, etc. Versus, hey, microservices are awesome. Highly decoupled, just add a new reward payment service, no rippling side effect, etc. So separate services give me great extensibility. So looks pretty strongly like separate services is the winner here, but let's do one more. What happens if we want to use multiple types for payment? We want to allow the customer to use some reward points, some credit card, etc. What does that look like? Well, for the single service, it's easy because everything is in one place. I can check to make sure it all balances out. I can do an ACID transaction in the database. No problems, headaches with that. For my separate services, Now I have to coordinate a payment across all these services, which means that now I need a coordinator. I need to add another component here to do this coordination across these services. And because it's a single transaction, I need to make sure that it all matches, that enough got deducted from each thing and that each of them got committed, which means I need transactional coordination across these databases, across these services, which is generally considered a bad idea in microservices. It's possible, but it's one of the more difficult problems you have to try to solve in microservices. So separate services give me performance and data consistency headaches, because now it's going to be way less performant with all this coordination. Data consistency is now going to be a challenge. It's not impossible, but I'm going to have to do some coding for that. And so now I have a better feel for what is the real trade-off analysis for this particular problem that I'm looking for. We still don't know which one of these we would choose. I'll come back to that later. All we've done so far is the trade-off analysis, but now it's not a clear winner because there are pros and cons on each side. We'll see how to actually make this decision in just a bit. But to go back to my scale, what initially seemed like a pretty simple thing, one service versus two services, is not all that strategic. It's not that huge a effort to do that, but the trade-offs are significant. And that's enough to push it further to the left than to the right. And so doing a trade-off analysis helps you determine where in this spectrum decisions like that reside. And this goes to our first law of software architecture, that everything in software architecture is a trade-off. This is, in fact, the distinguishing characteristic of software architecture. You could say that software architecture decisions are ones where each possibility has significant trade-offs. Because if they don't, then it's a much easier decision, and it's no longer an architecture level decision, it's much more of a design decision. But in our fundamentals book, when we wrote it, this idea of this first law, when Mark and I were writing this book, we started out, we really wanted to see if we could find things that seemed universally true in software architecture and codify these laws of software architecture. And we hoped there'd be like 10 of them, and it turned out there were 2 of them. We're actually going to touch on both of them today. This is the first one, that everything in software architecture is a trade-off. But there's a corollary that came with the first book. If you think you found something that isn't a trade-off, it just means you haven't identified what that trade-off is yet. This is true in software architecture, and very often people miss the important parts of trade-offs. Code reuse is a great example of one of those, because, well, code reuse is purely a force for good, right? Because the more we reuse code, that means the less code we have to write, and we're taking advantage of existing assets, and so code reuse is awesome, right? Well, but in a software architecture context, it has a trade-off. I often have organizations come to me and say, we love this idea of microservices, really highly decoupled architectures, and allows us to move really fast, so we want that. But we also want a high degree of institutional reuse. We don't want a lot of our teams writing the same stuff over and over, so we want to be able to reuse as much code as possible. And I have to be the bearer of bad news to break the news to them that, well, you know, reuse is coupling. That's how you implement reuse, is by coupling. So you cannot have a highly decoupled architecture and a high degree of reuse at the same time, because that's a trade-off between those two things. Everybody gets the first part of reuse right, which is abstraction. Oh, look, we could abstract this thing and use it from a bunch of places, but everybody misses the second important aspect of reuse, which is it also needs low volatility. Because if it has high volatility, if it's changing a lot and you're coupled to it, every time it changes, you have to stop and coordinate around that change. Even if it hasn't broken you, you still have to check to see if it's broken you. And so really reusable things are both abstract and have low volatility. But a lot of organizations miss that second trade-off, and then they end up coupling to things that change a lot, and it creates churn in their architecture. And we'll actually talk about a way to cut down on that in just a second. Mark and I are now in the process of doing the second edition of Fundamentals of Software Architecture, and we have now uncovered a second corollary to this first law. And you're the first audience to see this because this is literally just weeks old. And the second corollary is you can't just analyze trade-offs once, you have to do it over and over. And that's really the essence of this keynote. These decisions are intractable. It means that you can't just make this decision once and say, we're always going to use choreography in our organization. You have to do that trade-off for every time choreography comes up, you have to do that trade-off analysis again for reasons that we'll get into. And here's a great example, again, of the kind of trade-off analysis we often do in software architecture. We're looking here at an event-driven architecture, not necessarily microservices, because we're using a single database here. And this is a common question that comes up around communication between services in event-driven architectures like this, which is, I have this order placement service, and it needs to coordinate between payment and inventory. Here's the architecture question. Should the event payload include all the data necessary for processing or just the keys? We're actually talking about, I was at a conference in Denver recently, Venkat Subramaniam's Dev to Next conference, and my colleague Sanya from India, Vanya Seth, was doing a talk about all of these event-driven anti-patterns like anemic events and those kind of things. And this is a question that came up is, should you pass around keys or should you hydrate the entire contract? In other words, should I have order placement go to the database and hydrate the entire contract, all the information I need about that, and then take that contract and pass it to payment and have it do payment stuff, pass it to inventory and have it do inventory stuff, and then go back to order placement and have it right back to the database. So in other words, order placement's managing all this stuff, and it just reads it once from the database and writes it back once into the database. The alternative is to have order placement read the key for the relevant information out of the database and just pass the keys to these relevant services. Now payment will query the database to get the rest of the information it needs to do payment, and inventory will query the database to get the rest of the stuff it needs to handle inventory information, and then write that stuff back to the database individually. Which is better? Well, of course, it depends, but let's do a trade-off analysis and see what the really pertinent, interesting things are here. So for the hydrated contract, pulling everything out of the database at once, much better scalability and performance. I have a single database here. The fewer times I touch the database, the more scale I can get out of the system. That's going to be the bottleneck for potential scalability and performance. And so a fully hydrated contract gives me much better opportunities for performance and scale. But it now brings me to contract management and versioning. Now I need to manage this contract, and inevitably I'm going to end up having to version this thing. One of the blind spots that architects seem to have, so many architects seem to think that an architecture problem is sort of like a math equation on a whiteboard. And if you can ever solve that equation once, you just drop the whiteboard marker and walk away because that's a solved problem. But that's never the case, because software architecture lives in time. And it constantly shifts and changes and evolves over time. And so we solve this equation once, problem solved, but time is going to mean that payment slowly changes or inventory slowly changes. And now I have to start accommodating that change as those things happen in my software architecture. You are, I assume, all familiar with the 8 fallacies of distributed computing that Peter Deutsch coined back in the 1980s or 90s at Sun Microsystems. It's a list of 8 mistakes that you make when you move into distributed architectures. If you're not familiar with it, I highly recommend that you go to the Wikipedia page and learn these 8 things, because you will learn those 8 things one way or the other. You can either learn them from the Wikipedia page, or you can painfully learn them one at a time in your professional career and suffer the consequences. I think the former way is a much better way to learn them, but you do you. You can learn them either way, but you will learn those 8 things for sure. One of the things that Mark and I are doing is facetiously adding a few more of those to that list, which are observations that we've made over time. And I'll go ahead and tell you the 3 that we're adding. And number 9 is pertinent right here, which is versioning is easy, because it's not. It seems easy. Oh, just version it. Okay, great. But now, what is your deprecation strategy? How long is that version going to live in your ecosystem? How many versions are you going to support here? You don't want to be in the situation of a Salesforce.com, which is supporting 40 or 50 different versions of their API, because people don't want them to move off of it, so they have to keep backwards supporting old versions of their thing. When you deprecate these versions, how are you doing that? Is it at a service by service level? Is it system-wide? Is there coordination? So all these tricky things come up when you start talking about versioning. Just for completeness, I'll go ahead and tell you the other 2 that we've added. So that's number 9. Number 10 is that compensating updates always work. When you see presentations about microservices, they always whip out a magic wand and say, well, when that fails, then you do the compensating update. And shazam, it's magic. But you never get the follow-up question, what happens if the compensating update fails? Ooh, well, that's another problem that you have to worry about. So that's number 10, the fallacy that compensating updates always work. And number 11 that we've added is that observability is optional, particularly for distributed systems, because it's not. It's great if everything works fine, but when it starts breaking, you have no way of knowing how and why, and so you really need observability. So if you make this decision, you're going to end up in contract management and versioning, which is a headache. You're also going to end up probably with stamp coupling. And I want to dig into this a little bit, because this is one of the commonest problems I see in modern distributed architectures. People are constantly making this mistake in the modern world. And it's ironic, because this is such an old thing, this idea of stamp coupling. If you go to the Wikipedia page for coupling, you'll see this picture, which it's so old that it's actually quaint. This is from a book called Structure Design by Constantine and Jordan. This is so out of date, in fact, that the one on the far left there, which they call content coupling, your programming language won't even allow you to do that anymore. That's why you have private and protected and things like that in languages like Java. So this is from before structured programming. But I brought this up on purpose because the next to last one they have there, stamp coupling, is still alive and well in our world. Stamp coupling occurs when you share a composite data structure but only use parts of it. This is named from the COBOL days. This is how old this is. Because data structures in COBOL were so stable that they lasted for generations, literally. And when a new problem would come along and you needed to figure out which data structure to use, there were rubber stamps made, and you stamped it that this is the data structure we're using. That's the stamp coupling, is the rubber stamp. Because it's so stable, you can actually carve a rubber stamp out of your data structure. Imagine that in the modern world, but we'll leave that aside for a second. But here's how it manifests in the modern world. And it really comes from over-specified contracts. So let's say I have this profile service that supplies profile information for customers, name, address, etc. And I have a wish list service, and it's responsible for holding on to wish list items for customers. And wish lists have everything I need to know about a customer's wish list, including the customer ID for the wish list. What I don't have is the name of the customer, because that's part of the profile. And so when I make a request to the wish list service to be able to get the name of the person, wish list needs to do an inter service call to profile and say, hey, I need the name. But you'll notice the architect in this case has used JSON schema as a way of specifying this contract, and JSON schema tends to create really tight contract. We've bound all the fields up together as the default, and so when I get profile like this, I just get all the profile back and extract the name from it, and I get the information that I need. This is stamp coupling. I'm sharing a composite data structure, but only using a small piece of it. And here's why this is so bad. Because at some point, somebody's going to come along and say, hey, I notice you have state in your profile. Is that the full name of the state, or is that the two-letter state code? Because both those things are pretty common, and you're like, hey, you're right. That's misleading. It's supposed to be the state code. Let's change that to state code, which now changes the profile service and breaks the contract with wish list. Wish list doesn't care anything about states or state codes or anything like that, and yet I've now broken the communication between these two services because I've overspecified the contract and I've created a stamp coupling situation here. This is how you accidentally create brittle software architectures, where you change one thing somewhere and a bunch of things break in an unexpected way because you very often use stamp coupling and overspecified these contracts like this. And the point here is that looser contracts create less brittle software architectures. And in fact, this is the common advice. This is exactly where advice like from domain-driven design use anti-corruption layers. That's what that thing is there for, is to create a looser binding between things so that you can change the details behind it without breaking the contract. In general, you want as loosely specified a contract you can at bigger service boundaries. And so really tight scopes, you can have really specific contracts, but the broader the scope, the looser the contract you want, because the tighter it is, the more brittle it makes your overall architecture. And we have a problem with bandwidth as well, because this may be trivial in a non-distributed system, or a monolith, but when I start doing this at scale, this is going to have serious bandwidth implications, and I'm really passing around stuff that nobody cares about and wasting all of my bandwidth passing around stuff that nobody cares about. Obviously, this would be a much smarter contract if I just pass the name. That's all I know about profile service, is that it has names, and I don't care about all the rest of that stuff. And the last problem I have with a single contract is I have multiple systems of record here. Now, what happens if it changes in the database while I've got it hydrating and passing it around to all these other services? So I need to figure out a way to resolve that. So that's the trade-offs for the single hydrated contract. What about just the keys? Not as good as scalability and performance, because now I'm hitting the database a lot. Remember, I'm getting the key, and then I'm reading from each of the services and then writing from each of the services, so scalability and performance are not going to be nearly as good here. But single system of record, I have no data consistency issues. I'm implicitly sort of doing a last one in wins here, because if it changes while this workflow is going, I'm just going to get that change and update it as well. So the database is the single of record here. I don't have a more than one system of record here. No stamp coupling, bandwidth, or contract management issues. I'm sending around the least amount of information I can, so I don't have to worry about those things. And so here is the matrix that we're able to put together for, okay, the hydrated contract, much better for scalability and performance, but issues otherwise. Single key, not as good as scalability, but has fewer headaches associated with it. This doesn't automatically mean one or the other of these is going to win, but now we've done the trade-off analysis. Now we can go to the business or the stakeholder or the real decision maker and say, okay, how important is scalability for this solution? Does it need to be really scalable, or can we mitigate that in another way? If it doesn't need to be super scalable, then we clearly can see that passing a single key gives us fewer issues to have to resolve. So that's how we figure out how to resolve those kind of trade-off analyses at the back end. Again, you can't just analyze trade-offs once. You have to do it over and over, because we can't say, oh, in distributed architectures, always pass the key. Because in a different situation, there may be different trade-offs that come up and different values associated with them. So the name of this keynote is What Makes Software Architecture So Intractable? Maybe it would be better if it was, how does one make software architecture more tractable? Rather than yelling at what's wrong with it, how do you actually make it better? And so let's talk about that. And the mechanics part of my talk, and this idea of architectural fitness functions. I talked about this last year, was the entire focus of my keynote. I'm only going to touch on this briefly here. That leads me to the next thing. So the idea of an architectural fitness function, we created this idea. The original idea for this was Dr. Rebecca Parsons, who was the CTO of ThoughtWorks. She told me this idea about 10 years before we wrote the book about it. She had this great idea of applying evolutionary architecture concepts to software architecture, this idea of guided change and fitness functions, this idea of an architectural fitness function, which you can think of as sort of like a unit test, but for architectural characteristics. So when you think about how do we manage the evolution of our problem domain to make sure that as we build new features in our ecosystem, we don't break all the existing stuff that's already there? Well, we have a lot of mechanisms for that. We have unit tests, we have functional tests, we have user acceptance tests. If you're a big enough company, you have an entire division of your company called QA who's responsible for making sure that as you add new stuff, you don't break what's already there. What we need is a QA department for software architecture concerns. Right now, some of you have a few ad hoc tests for important things in your software architecture, but nowhere nearly as comprehensive a test harness as you have around the domain parts of your system. You have interlocking verification mechanisms for modifying changes for your domain, and very often none for your software architecture characteristics. That's really what these are, the same level of automated checks for the important architecture characteristics that you have. But it's not nearly as simple as unit testing and functional testing, because fitness functions may encompass a large number of things, like software metrics, software quality metrics, for example. This is going to come up again in a big way, and in fact matches the theme of this conference. One of the things that you can validate with architectural fitness functions are internal code quality, coupling, cohesion, distance, normalized distance to the main sequence, etc. I'll revisit why that's increasingly important right now in just a bit. We have unit testing libraries, some of which I'll show you in a second, for writing, checking parts of your architecture. Very often we use things like monitors, because how are you going to validate operational behaviors like performance or scalability or elasticity? You build monitors. Now, just putting a monitor in place doesn't make it an architectural fitness function. Putting a monitor in place that fails when it reaches a threshold or some other anomalous condition is the objective measure that converts a monitor into a fitness function to validate that, yes, performance is what we think it is. Chaos engineering, which was pioneered by Netflix, is a perfect example of this idea. This was the Simian Army, which were mechanisms that run around in their production environments and simulate breakages so that their developers are forced to write code that handles those things, whether simulated or real. The code still handles it in either case, and it worked really nicely for them. And we've seen, since we wrote the first edition of our book in 2017, we've seen a growth of this category of tools, and in fact, a whole lot of tools to allow you to do this kind of stuff. And let me give you a very simple example, and then we'll extend this example. One of the things you want to try to avoid as in a component-based system, any system that's big enough to be reasonable is component-based these days. And one of the things you want to try to avoid in a component-based system are cyclic dependencies between the components. That's where one component relies on another component, which relies on another component, which relies back on the first one. This is an anti-pattern in architecture because you can't just reuse one of these components. If I want to reuse one of them, I have to take the whole rat's nest with me. And if these are also bound up with other components, then before long, my entire architecture is just one big ball. This is a great example of a structural fault. You know, when you see a big bridge by an interstate, a single micro crack in that column is not dangerous. 1,000 micro cracks in that column is extremely dangerous. And this is exactly one of those things, this sort of little structural decay within your system. When I was younger, I always heard this term as bit rot, but Wikipedia seems to think that it's called system rot. But you may have heard either of those. System rot is the assumption that a piece of software that's old must be terrible inside. That it has somehow eroded or rusted inside because of its age, that the older it is, the worse it must be. And a lot of it is because of this kind of stuff. These little tiny faults that creep in over time that by themselves are not critical, but in aggregate are deadly. But how do you prevent this from happening? Because the way this comes about is you're typing along and you reference some class you've never used before. What does your IDE do? It pops up a dialog that asks you if you want to auto-import that thing, and you swat that away so fast, you don't even read that dialog anymore. It's like a sneeze reflex. You don't realize this, but they changed the text on the do you want to auto-import this? On that little dialogue, they changed that text to a nursery rhyme 5 years ago, and you never noticed because you haven't read that thing in years. You know that as soon as that auto-import dialog comes up, your job is to swat that away as fast as possible and keep coding. Most of the time, that's okay. But every once in a while, it's doing this. How do you prevent that? You build an architectural fitness function and wire it into your continuous build. This is using a very old metrics package to do this. I want to show you a newer tool to do this. ArcUnit and NetArcTest will both do this. A variety of tools like SonarQube will do this kind of check for you. You wire this into your continuous build, and now you don't have to worry about developers accidentally creating cyclic dependencies between your components as they're building your software. This is a way to validate really important architectural concerns in an automated way over time. There's a whole family of tools that have come out to do this. ArcUnit is the most mature of these in the Java ecosystem. This lets you define relationships between things, and so you can say coding rules like who can use standard streams. You can do things like maybe one of the things that's annoying you is that lazy developers are throwing generic exceptions instead of properly subclassing exception and throwing that. You can prevent that from happening. These are built-in governance rules that already exist in ArcUnit. But it also lets you state what you want the intended structure of your code to be. Let's say that you decided you want a layered architecture with a presentation layer and business rules and a data access layer. The reason you choose this as an architect is separation of concerns. I want all of the data access code to be in that data layer. And you design this architecture, but you hand this over to a group of developers to implement it. How can you make sure they're going to implement this correctly? Either because they don't understand the importance of this, or maybe you're in an organization where it's better to ask forgiveness than permission. And they're just going to do it because they're in schedule pressure and hope you won't notice until it's too late to fix it. How do you preserve this kind of architectural structure when developers have to actually implement this. And when we go back to our architecture versus design criteria, this is serious, because if they start cheating on that rule a lot, you no longer have a layered architecture, you have a big ball of mud, which has no discernible internal structure. The way you fix that is by writing a fitness function like this in arc unit. No classes that reside in a package service should access classes that reside in a package controller. You wire this into your continuous build, and now they will honor the purposes of the layers that you've created in your architecture, because now you've governed those in an automated way. This allows architects to define the sort of scaffolding of what they want their architecture to be. This is what components should look like, and this is how they should communicate, and then leave the implementation details to developers within the scaffolding they have created. This also exists for the .NET world, and NetArchTest. It uses the same kind of family of Hamcrest matchers, these kind of fluent matchers like this. These are all examples from the .NET NetArchTest. But here's the thing you really want. You know, things like cyclomatic complexity tests or arc units, great, but those are compilation units. That's a single code base. Here's what I really want to govern. I have 3 microservices with an orchestrator. The orchestrator owns the state of this workflow. Therefore, I do not want these domain services talking to each other and updating the state, because the state of the workflow will get out of date with the orchestrator. So the rule that I want to establish as an architect is that these domain services only talk to the orchestrator and nobody else. Where's the slick tool or framework I can download that lets me write the fitness function to do that? Unfortunately, it does not exist. And this is where we as developers and architects have gotten sort of lazy. When I first joined ThoughtWorks almost 20 years ago, which is shocking, one of the things that we had to do a lot was to stop people from building new frameworks and libraries. Every time a new problem came up, they would roll up their sleeves over the weekend and start hacking away an open source solution to whatever this problem was. And the problem was, look and see if somebody else has already done one, because there's probably 15 out there in the world. Check first and see if one's already there. The pendulum seems to have flipped to the opposite side now, where you tell people, oh, this is the problem I need to solve, and their first question is, oh, where's the comprehensive library I can download where I can set up to, but not over 5 configuration parameters and have it do exactly what I want? Oh, that doesn't exist? Well, that's not a problem worth solving then. I can't build something from scratch to do that. The problem with this, though, in architecture, and generally in architecture, is that, okay, well, let's say that this tool exists. How would that tool for this have existed? Because you don't know what kind of platforms you're writing this in. And in fact, they may be all different platforms, because this is microservices. We can do all kinds of different platforms, tech stacks, etc. Different databases, different communication protocols. How can we tell? The point here is that most of these architecture fitness functions are not big elaborate framework sort of things, but instead the first question you have to ask yourself is the information I'm interested in available somewhere here? And the answer is yes, of course. All of these services know exactly who they talk to and who talks to them, so you force them to write that information out into a log, and you write this in a scripting language. For each one of those services, import their logs for the last 24 hours and see who they're talking to. This is actually written in Ruby. Almost all architectural fitness functions are not written in the platform or tech stack you're writing the solution in. They're little scripting languages or little throwaways, shell scripts, or things like that, because all you're doing is combining information that's already available somewhere in your ecosystem to learn something about it. And this is exactly what this does. This is a really, really trivial kind of fitness function to write if you can assume that all of these parts of your ecosystem have observability. This is Ruby, but this could be any small scripting language to do this. And that's this idea of architectural fitness functions. And these could be used to describe all parts of your ecosystem. Things at the source code level, including code quality metrics, including coupling, architectural structure. These can describe characteristics of integration architecture and how pieces fit together and how they should fit together, all the way up through things like enterprise architecture and how those things should be expressed, those kind of strategies from an ecosystem standpoint. Fitness functions allow you to define all of those things for the capabilities you want to support in your organization and well-defined contracts to prevent brittleness across your ecosystem, which of course can also be governed by this idea of fitness functions. This gets to the subject of mine and Mark's next book, which is going to be this idea of architecture as code. We now have reached a maturity in the software development ecosystem where architects can start designing in code the scaffolding they want their architecture to look like, what dependencies should exist between components, what kind of architectural structure you should design in your system, and build those as part of continuous governance so that you can, in fact, define your architecture in a discrete and a declarative way. So that's coming probably about this time next year. So I want to wrap up with a few trade-off analysis traps to try to avoid in software architectures. I mentioned before, how do we reach one of these decisions? We do the trade-off analysis, but then how does the decision come about? Well, you need input from friendly groups of people that look like this, that control your organization, who adds value. And they decide time to market is the most important thing. You as an architect go through an architecture characteristics analysis and you find maintainability, testability, and deployability. Then you do a trade-off analysis. Time to market really means maintainability, testability, deployability. We do the trade-off analysis. We find that maintainability versus performance is the trade-off. We then reconcile that back to what the goal of the business is, and that's how we ultimately reconcile that decision as to which one of these should we choose. And let's see what this looks like. And this is a common trap to try to avoid, the out-of-context trap when you're analyzing trade-offs. I have a software architect here who says, I can't decide whether to use a shared services for the common functionality or a single shared library. A single shared library gets compiled into each of the services, whereas a shared service uses inter-service communication. I don't know. Could be either one, so we'll do the trade-off analysis. You end up building a lot of matrices like this as software architects. And in fact, the real skill in your organization is what populates that left-hand column. These are the things that are important to my organization. So that's the thing that's very organizational specific. But in a general case here, we can say, okay, heterogeneous code, tougher for the shared library because every time I change that, I have to have a different version for each platform that I use, whereas shared service, nobody cares, it's just inter-service communication. Really tougher if I have high code volatility for the shared library because every time that changes, I'm going to have to change and redo that, recompile my services, whereas they just get the newer code in the shared service. I can version changes in the shared code more easily. Now I've got to do runtime version resolution for the shared library, which is tougher. Change risk is less because if it compiles successfully into the library, it's probably good to go, whereas I have runtime errors that can happen to the shared service. Performance is better if it's compiled into the library, and I don't have to take the inter-service communication hit. Fault tolerance is better because it is compiled into that library. And finally, scalability is better because I'm not doing inter-service calls to get to that thing. And so if I just count up the pluses and minuses, looks like the shared library is the winner. And this is the trap. It's often a mistake to assign the same weighting to all the things on the left, because some of those things may be more important than others. And in fact, we have services written in 4 different languages in our ecosystem. Performance and fault tolerance aren't big deals for us. We really want to manage frequent changes to shared functionality. Now, if that's the case, even though it looks like the first one is the winner, the second one actually meets this criteria better. And this gets back to this idea of having to do this trade-off analysis over and over and looking carefully at the ecosystem. The next tip is something that we ended up doing in both our fundamentals and our hard parts book, using qualitative analysis to iterate on design, leading to quantitative analysis. And here's what I mean. You know, I can't choose which distributed architecture style will be the most appropriate one for the new system. So one of the options you have is to go to your boss and say, boss, I have good news and I have bad news. The good news is I'm going to choose the perfect distributed architecture style for the new accounting system, and I'll be able to objectively prove that it's the best architecture style for the new accounting system. That's the good news. The bad news is it's going to take me 4 times longer than you had allocated for it and 4 times as much money, because I'm going to build it all 4 ways, measure each one of them, and throw away the 3 that don't work as well. That's great. Objectively, the best possible implementation for the accounting system. And if you work in that place, congratulations. You are going to be able to build some awesome architectures in that place. But you don't work in that place. So how do you make these decisions without actually building them? This is this idea of qualitative analysis. And Mark and I did this in our fundamentals book for architecture styles. We gave star ratings to each one of the architecture styles as to how well they handle particular architecture characteristics. These are qualitative ratings. We didn't build all these systems, but we said, well, you know, this one has more of this particular characteristic than this other one, and so we ended up with this 5-star scale. And now we can look at the sweet spots for each of these architectures. What do they do really, really well? And then go back to what the purpose of this analysis was. Time to market is the most important thing here. So which of these architecture characteristics most affect time to market? Maintainability, deployability, and testability. And it turns out that microservices scores the best one here. This is the trade-off analysis and the reconciliation with the purpose of that trade-off analysis. You know, I'm not sure which transactional saga to use for this new system. This is something we did in our hard parts book, where we modeled all 8 different possibilities and gave ratings for each one of them as to the combination of forces. And this actually tells you some interesting things, because, okay, time to market is our most important thing. Time to market is not one of the criteria here, which often happens, but complexity is. And if it's a less complex system, it's easier to get good time to market. And so this allows you to look at the priorities that you have and to align those with the decision process that you're trying to make. Once we've made these decisions, of course, now we want to go and create this idea of architectural fitness function so that we can actually measure those things. Because this serves 2 purposes. One, it tells you what's happening in your architecture, but it also helps you hone your estimation skills and get better and better at figuring out how well I've done with this particular problem set. We talked about this before, modeling relevant business use case scenarios, but what we didn't do was wrap it up in the end. We did the analysis, but we didn't have this key part. And this is what tells us, ultimately, because maintainability, testability, and deployability are our most important things here, the decision that we need to make here is for that one, and we need to figure out a way to mitigate the headache of having that composition, or rather transactionality, and having to deal with that from our ecosystem. So I'm not going to Well, let's talk about that. Last one of these, don't over-evangelize a particular solution. You always end up in trouble if you do that. You should always use publish, subscribe, broadcast messaging. It's way better than point-to-point, and here's why. So if you're using point-to-point messaging with message queues and you want to extend it, that means that to extend it, you have to add a new queue, and you have to modify the bidder, and you have to add a new contract, which is a big hassle. It's better if you just use topics. That way, if you add a new consumer, you just subscribe to that topic. No changes to the bidder, no changes to the bid, any of that stuff. So much nicer, cleaner, easier. So wow, you're right. That's the way we should go. You always end up in trouble when you over-evangelize like this, because then the narrator's voice comes in and says, meanwhile, a little while later, oh, I can't create separate contracts for each of the services, and guess what? We have stamp coupling all over the place now. I make one change in that contract and it breaks a whole bunch of stuff, which is annoying. Oh, we just had a security breach because everybody has access to everything on this topic. There's no filtering. And oh, look, I can't use auto-scaling because you don't have queues, and that's the only way you can do auto-scaling. You can't do that on topics because each one is an equal citizen. This is the danger of over-evangelizing something. It always ends up coming back to bite you. So these two things together really account to governance. And I'll leave you with one last thought. And this is apropos to the theme of this conference. As architects, get ready for a tidal wave of functioning but terrible code. Because Gen AI, when it generates code, it does so with brute force, and it works, but it's terrible. Get ready. It's coming in droves. And what you can do is build automated fitness functions to look at the AI-generated code. There are a lot of well-known internal code quality governance tools like psychometric complexity, like abstractness, like instability, like normalized distance to the main sequence. When we first came out with the Evolutionary Architecture book, most architects sort of, yeah, developers know you shouldn't do this stuff, but Gen AI doesn't know you shouldn't do this stuff. So this is your safeguard against functioning but terrible code, which is great if you're going to throw it away, but if you're trying to build a foundation for something, you want that code to be of high quality. This is a way you can automate that, because you will never be able to manually outpace generative AI in its ability to create code. You have to automate this. And that's this idea of automating architectural governance. And that's part of what makes it so intractable and how you can hopefully fix it. Thanks so much for having me. Thanks. Thank you.
Thank you, Neal.
My pleasure.
Yeah, it works? Works?
Yeah.
Yes. Perfect. So I think that we will need some distance between us, so there is no echo. We are running out of time, but there is one question that I would like to ask, because the application gets frozen. This is the only question I can see. Which is the trade-off analysis between having domain services talk to each other when compared to having the orchestrator in place and domain services talking only with the orchestrator?
Who does that? Is that the question? So if you want the answer to that question, that is, in fact, the entire second half of Software Architecture, the Hard Parts, the book. It really deals with what happens when services call one another. And it turns out that you can't just do individual analysis on communication or coordination or consistency, because it's a three-dimensional conjoined space. And so every time you tweak one of those, it tweaks the others. And so that's the whole basis for that saga analysis. So there's no simple answer to that question. There's a huge amount of trade-offs depending on sync versus async, coordination, is it choreography versus orchestration, and consistency. Are we trying to achieve atomic consistency or is it eventual consistency? All of those things flip all sorts of trade-offs. So that's why you have to do those trade-offs over and over again. And you can't just say, oh, we should always use choreography, because that'll work sometimes, it'll be a disaster sometimes. And you have to do the trade-offs over and over.
So thank you. A big applause for Neal.
Thank
Thank you.
Thank you.